Good afternoon, everybody. This is the Water and Energy Efficiency webinar at the Alliance to Save Energy. I hope everyone can hear us and that you're able to follow us on your screens. My name is Robert Bruce Lung. I'm a Senior Program Manager at the Alliance to Save Energy. And if we can move down to the next slide. You'll see a quick agenda that we're going to try and follow as closely as possible, although there may be some deviations. We ask that you hold your questions until the end, where we'll have a question and answer session of about 30 minutes. As we begin, it's my distinct honor to introduce Mr. Brian Castelli, Senior Vice President at the Alliance to Save Energy. And Brian will talk to us about the importance of water and energy efficiency, as well as the history of our Watergy program.
Great. Good afternoon, everyone. I'd really like to talk about what the Alliance is first. And we are a national, international, not-for-profit organization. We were created in 1977 by two U.S. senators, Senator Charles Percy and Senator Hubert Humphrey, a Republican and a Democrat. We've been a bipartisan organization ever since. We always have a sitting U.S. Senator as our honorary chair, and that current chair is Senator Jean Shaheen from New Hampshire. And we always have one of our associates, and we have about 178 associate members. We have one of the CEOs as a co-chair, and our current co-chair is Peter Darby, the CEO, President, and Chairman of the Board of Pacific Gas and Electric. We have 13 members of Congress who serve on our board, and they are active. They all participate in meetings. They participate in various functions that we do, and we basically work in our associates are also in the environmental field, the consumer advocacy field, they're trade association heads, state and local policymakers, corporate executives, utility companies. So it's a large group. This slide shows just some of the logos for the companies that are our members, and they really represent all the economic sectors that are involved in energy efficiency. Our initiatives that we do here at the Alliance include research, we do policy advocacy, we do education from K through 12 through to the university level, and technology deployment, market transformation, and communications and outreach. Those are the big areas. We run programs. So let me jump now into what we're really here to talk about today, and that's the energy-water link. Now, energy and water are linked in many ways. Energy is needed to extract and convey water to the residential, commercial, and industrial end uses. We need energy to treat the water. We need water that's needed in electric generation for power plant cooling. Energy and water are getting scarcer. That's a fact. Drought conditions in different parts of the world, increasing energy costs, and population growth are also adding to the demand. Energy efficiency gives us some great opportunities to save both water and energy. Improving motor systems, implementing energy management and design systems, installing system automation, metering, leak management. These all are opportunities in the link for energy and water where we can get greater efficiencies. Energy production, for example, often depends on the availability of water. One, just for hydroelectric power plants, or two, the cooling of thermal electric power plants, and that's something that uses a lot of water. Now, treating water for human consumption and moving the treated water is an extremely energy-intensive undertaking. Each liter of water that passes through a water system represents a significant energy cost, and it represents an energy cost even if the water doesn't reach the ultimate consumer. So if you have leaks in your system, leaks in the transmission, you still are paying an energy cost for that lost water. Now, in the next slide, we're going to be looking at water production and energy use. Water delivery and wastewater treatment are extremely energy intensive, as you can tell from the purple bar. Water quality standards are becoming stricter, so more energy is needed to treat the water. And as population grows, more energy is needed not only to convey water to more people, but also over longer distances. So every year in the U.S., we have 5,100 miles of piping added annually just to get the water from the source to the plant. So those are all important aspects. Some of the challenges we see begin with leakage. As I just mentioned a few seconds ago, leaks waste energy and water. And in many distribution systems around the world, we find many, many leaks. We find them in industrialized, developed countries where infrastructure is old. In the U.S., we have almost 1 million miles of water distribution piping. And based on survey data, 3% of all that piping is more than 30 years old. We witnessed some, at a conference recently, of pipes that are still active in an eastern city that were put in the 1830s. So we are talking some old infrastructure. Each year we have more than 237 breaks in water piping. 3,590 miles of piping have to be replaced every year, and we need a lot of additional pumping capacity to overpower the demand that's caused by the leaks. So, you know, what we have is, in many, many systems, the operators of the water utility have to deliver water. So when they have leaks, they aren't delivering as much water, so they increase the pressure to put more water through the pipes. They increase the pressure, they increase the leak. So you have a circle that becomes unbroken. Unfortunately, it keeps leaking more and more. So I think the next slide, if you're going to talk a lot about wastewater treatment and energy use. As you can see, aeration is a big part of the energy use in treating water. It accounts for more than half of the primary energy use that's needed. Now, you know, you have these activated sludge processes that have to use fans and blowers, and they use a lot of energy. Pumps also consume a large share of the energy, and they require about 15% of the total plant use. Heating and solids dewatering are processes employed to treat solid waste matter that's been removed from wastewater streams. Other processes, such as chlorine mixing and effluent filtering, use about 4% of our consumed energy in this water and energy field. Wastewater treatment and energy use is a very interesting topic. The aeration blowers account, again, for the majority of the wastewater facility use. Manual control of fixed-speed aeration blowers can cause up to 50 to 60% of excess energy use. So variable speed controls, variable speed fans, variable speed motors are really critical. Unfortunately, most of our infrastructure uses the same motors that have been there for the last 30 or 40 years, and they aren't variable speed. System controls on aeration blowers also improves aeration efficiency better, and we really have got to look at this area when we talk about energy and water. Now that leads us right up to the topic of today, which is Watergy. Watergy is a name that the Alliance began using around 15, 16 years ago when it created this program to link water and energy. And what it does is we try to maximize the efficiency of both energy and water at the utility level. Each gallon in our system requires energy. It's pretty easy to get 20% or more energy savings off of a typical system in the U.S. Water and efficiency frees up funding for other crucial public services. This is really critical, because if you're a city manager and your water utility has huge water and energy bills and you can cut those bills, then you're freeing up you're freeing up dollars that can be used for education, can be used for other infrastructure within the city, within the municipality. So this is a good way to really free up funding that you wouldn't have otherwise. Mitigating risk in increasingly water-constrained environments is critical even today. It's going to be more critical later and down the road. So what does a Watergy project involve? It involves an assessment of the main end-use application. It involves assistance with design for energy efficiency, where we look at the system holistically, look at every piece of the system, and we then look at how can we add controls and sensors so that the operators know what's happening at any point in the system at any given point in time. Our Watergy program also includes an energy management plan, but also training for plant personnel. And we find that the training for plant personnel starts right at the beginning of a project. You bring in the plant personnel immediately. That gets the kind of buy-in that you're going to need as you go through this assessment project and implementation of the actual measures that need to be done. We also look at ways to finance the mechanisms you need to enable the implementation. And again, there's a lot of good opportunities for outreach and recognition by the constituents of the water utility. So that's important. In the beginning, Watergy was funded at the Alliance by a USAID cooperative agreement that began back in 1997. However, after the 10-year cooperative agreement was over, we found a number of different sources that are providing funding for this program. The funds include everything from other donors, such as the Inter-American Development Bank, APEC, the Asia-Pacific Economic Cooperation, but more importantly, private companies like Coca-Cola and local utilities themselves are now funding these projects because they've seen the benefits of the 10 years of experience that we had with our international program. Our Watergy goals are to achieve energy and water and monetary savings through technical and operational changes in water supply systems. And we want to provide consumers with quality water while reducing water and energy waste. And this also really helps the municipal and city governments, because if you're paying for water that's wasted, that leaks out, that's not delivered to the consumer, then you have that additional water available for new consumers, and you're not having to pay for any new water as well. So there's another savings benefit here, and I think that's really critical. In the past few years, we've opened up offices in South Africa and Mexico that focus on Watergy projects. Both of those offices get funded by either private corporations now or municipal governments and water utilities. So that's been a great change from getting off of purely government-funded projects to funding in the private sector. And I think our projects have typically involved the pump system efficiency upgrades. Managing leaks is a big part of it. The automation and the sensors and controls, establishing the metering and monitoring systems are just critical to the utility itself, because it knows then what it's delivering and what it has to do. Now, I'd like to talk a little more about our historical success. Beginning in 1997, we worked in over 100 cities in more than 16 countries. Some of the countries are listed there. In many of the developing countries, up to half of the water produced is lost in leaks. That's an amazing statistic, but it's a true statistic. Paybacks are rapid, usually from a few months to up to 3 years. So even if we put in $2 or $3 million of work and equipment, the payback is less than a year, and that's a pretty great return on investment. Our aggregate results have been about 20.8 million kilowatt hours of electricity saved and $5.3 million annually in savings on these projects. And just this past year, we launched our first Watergy program in the U.S. in Bucks County, Pennsylvania. And it's really been heartening to see that we have interest in the U.S. now for a program that's been existing for 13 years, 14 years almost in other countries. The projects we've run around the world, as you can see, it covers pretty much all the continents. We have projects in India, Ukraine, Kenya, South Africa. But we've also done training on what Watergy is, and we've done it at the level of plant operators. We've done it at the level of mayors of cities. Last year we ran a training program for 25 mayors in China. It's becoming a big issue worldwide. Our next slide is a case study in Mfuleni, South Africa. In Mfuleni, the problem was 80% of the water flowing to the homes was lost through leaking main pipes and plumbing fixtures. That's 80% of the water. Now, if you think about that, that means for every 100 gallons of water or 100 liters of water that flowed through a system, you only ended up with 20 getting to its ultimate consumer. That is a huge penalty on the energy it took to pump it through the system. Aside from the fact you've had to provide all that water and it's just lost. So the technical solution started with pressure management. We looked at automated pressure management valves on each supply line. We reduced the high bulk pressure. Further reductions occurred at night, a demand type program, demand response program. And we commissioned $800,000 in construction in September 2005. Financing solution was really unique here. We used a performance contracting type solution. We had a build, operate, train, and transfer company that came in, owned the system for 5 years, and then turned it over to the municipality. The fee was that the firm got 20% of the savings. So the municipality didn't have to put out any money up front. This was a great system, and the water pressure management firm acted as an ESCO, an energy service company, which are very typical here in the U.S. The picture of the Olympic-sized swimming pool is the fact that every hour the leaks, the 80% leakage, would fill 2 of those pools every hour and would frankly fill a small reservoir in a year. We can go on now. The Mfuleni results, our payback period was less than 3 months. The annual savings were $3.8 million, and water savings were over 2.1 billion gallons, or greater than 30%. Energy savings were 14 million kilowatt hours. And added benefit was the CO2 reductions. More than 12,000 metric tons per year were saved. So this was a great project, and one in which, it really shows the benefits of this program. A second case study is one we did in Fortaleza, Brazil. Here, many households weren't even connected to water service. There were many inefficiencies: pumps, operations and maintenance, systems management. The utility couldn't afford the energy costs. So our project brought in automated controls and sensors on pressure and pumping. We improved data collection and analysis, and we improved motor efficiencies. The automatic controls and sensors are basically like a SCADA system in the electric utility industry, and it gives the operators immediate knowledge of what's happening at any point in the system so that they can divert flows or they can cut off valves, and it's a really important part of an overall system approach. Now, our results were pretty amazing here, too. 88 million kilowatt hours saved over 4 years, and this utility added 88,000 new connections but using the same amount of water as they had before we did the project. We had $2.5 million saved every year, and the investment we had was only $1.1 million. So the simple payback was 7 months. That again is a pretty amazing case. So let me just reiterate now, the cost-effective actions in a Watergy program are improving the efficiency of pumping system, leak detection, repair, and lowering pressure, automated controls, energy management, and metering and monitoring. Those 5 areas are the areas where you do have quick paybacks and you improve the system efficiency to an incredibly high degree. I think I'm going to turn this over now to Mary Ann Dickerson. So Mary Ann, you're on.
Hello, my name is Mary Ann Dickinson, and I'm the President and CEO of the Alliance for Water Efficiency. I'm very pleased to be here today participating in this webinar to talk to you about the combined water and energy benefits of doing customer-side water conservation programs. The Watergy program has done a terrific job over the past years educating water utilities on how they can save energy by optimizing their treatment and distribution system operations. I'm here today to talk to you about what kind of benefits can be experienced by doing the same sort of thinking on the customer side and reducing demand on the customer side. Let's first start by talking about water use in the U.S. The U.S. Geological Survey every 5 years does a water withdrawals report, and the most recent report, which was recently released, indicates that in the year 2005, 410 billion gallons of water were withdrawn in the U.S. Now, this is water withdrawals, not consumptive use. But the statistics are still worth evaluating because of those water withdrawals, 49% of those withdrawals are related to power plant cooling. And that means that water resources in the U.S. need to be available for this purpose. There is a significant water footprint to energy and electricity production. And that is obviously a factor that needs to be recognized in siting power plants and in managing power plant operations. The next highest withdrawal is 31% for irrigation, which encompasses mostly agriculture, but also urban landscape irrigation. And the third largest user is public water supply, which is 11%. Of this water withdrawal pie chart, 85% of it is freshwater and 15% is saline. So that's kind of how the statistics break out in the United States. So how does that actually relate to what we're looking at in terms of consumption? Well, the first thing we need to look at is where there are areas of the country that are experiencing drought and shortages. This is the most recent U.S. Drought Monitor map that was downloaded as of June 21st. And in this map, you can see that large areas of the southern part of the United States are experiencing D4 exceptional drought conditions. Texas in particular is being very hard hit. When you download the map at various times in the year, it will always look different. There will always be regions that are in drought at one point and perhaps not in others. But what this analysis really shows us is that where there are serious drought issues, there need to be additional measures taken to optimize water use and reduce wasteful activity. But lest you think that this kind of drought is restricted to these areas of the country or just the arid West, take a look at data that was prepared by the U.S. Government Accounting Office in 2003. They conducted a survey where they asked individual states when they were likely to experience a state, local, or regional shortage by the year 2013, which really is 2 years from now. 36 states responded positively, as indicated in the color coding. 2 states said they would have statewide shortages. 16 said they would be experiencing regional, and local shortages were reported by 18 states. But there were a number of states that did not respond. 3 of them, California, Nevada, and New Mexico, I would argue are always in a continuous state of some kind of shortage. And so I would argue we should add those 3 states to our number, making it 39. And if you take a look at Alabama, which did not report a shortage in 2003, would very likely now say that the area around Birmingham is experiencing periodic shortages. So that makes 40. 40 of the 50 states are in a situation where water supply shortages are imminent or likely. How does this then relate to energy? Well, if you take a look at this very well-distributed graphic from the California Energy Commission report, you'll see that each stage of that water supply and treatment and wastewater treatment and collection cycle is energy intensive. In 2005, the Energy Commission in California released an analysis in their Integrated Energy Policy Report that included an entire chapter on water, both urban and agricultural water usage, and documented what they saw as ranges of consumption, energy consumption on a million-gallon basis. So adding up the entire water conveyance, treatment, distribution, end-use consumption, wastewater collection, treatment, and discharge yielded a range of 2,000 to 20,000 kilowatt hours for every million gallons of water produced. This is a wide range, but it's also a very significant amount of energy. And with high embedded energy values in water supplies, utilities need to take a look at how best to reduce that energy load. Especially important is this pink area of end-use consumption, which basically shows that the customer is also an opportunity for energy efficiency and savings opportunities. So in California report, they basically added up what the sum total was across the systems in the state, and they concluded that 19% of their electric energy load was related to the pumping, treatment, movement, and end-use consumption of water, and 32% of the natural gas load was similarly related to it. So these are sizable numbers. They indicate the enormous opportunity that exists in the water supply and wastewater treatment community for reducing that embedded energy load. But probably the most surprising finding for me was learning that 95% of the state's energy efficiency goals for that next 3-year period could be met by just funding water efficiency and at a lower cost, at 58% of the cost. So again, astounding findings, and the real question is this typical of states around the country, or is California an anomaly? And although we do see there's lots of skepticism about whether these numbers can be replicated, there is clear knowledge that these numbers need to be analyzed for various regions around the country. We don't know what the numbers are regionally or even nationally, and this kind of analysis that was done in California needs to be done elsewhere. So one organization did attempt to do that. River Network, which is a nonprofit organization based in Portland, national organization, took the California Energy Commission methods and applied them to past studies that had been done by EPRI and others, and concluded that 13% of the nation's electric kilowatt hour equivalent electric energy load was related to water and energy use. So that if we were to take what California reported as 19%, that a national average might be as much as 13%, which is orders of magnitude higher than what had been originally estimated. This is a crude estimate. We clearly need to do something a lot more detailed, but it points up the need to actually take a harder look at what's going on at the local level. And what the report does that's interesting is it explores potential for energy and carbon emission reductions through demand-side, water-oriented approaches. So if you're interested in the report, there's the URL for it, rivernetwork.org. So when we talk about those water and energy savings opportunities, what are they? Well, hot water emerges as, of course, the clear, obvious choice. You're heating water to render it to a high temperature that takes energy. So where you can reduce hot water usage, you're reducing energy. And a lot of these programs have been funded by energy efficiency funds in the past. So these are the kinds of activities in both the residential and commercial sector that basically deal with reducing water use. Clothes washers, shower heads and faucet, aerator retrofits are easy ways to reduce consumption while not asking the consumer to change any of their behavior. water and energy audits can also identify where additional opportunities for saving water and energy can occur. But a largely ignored area is the commercial area, where certain sectors like hospitals and food service have very high water and energy footprints, and where commercial clothes washer replacement, commercial dishwasher replacement, connection with steamers, pre-rinse spray valves, these are all devices that greatly reduce the amount of hot water that's used overall. And combined water and energy audits in the commercial sector, particularly for cooling tower management, are a terrific opportunity for maximizing those benefits. But let's not forget the cold water side. I think historically energy efficiency programs have not funded cold water programs because they did not believe that the embedded energy was worth funding. But by ignoring the embedded energy in cold water, they're ignoring multiple benefits from that treatment and distribution. A high-efficiency toilet does more than just save water at the consumer end. It also reduces flows for the wastewater treatment system and has the potential to extend the life of existing systems that might be capacity constrained, or has the potential for consolidating and creating lower treatment costs. Landscape irrigation efficiency is another opportunity to greatly reduce a water utility's summer peak, a peak that has been largely growing in systems across the country, and often systems have to be expanded to meet peak demand that sometimes is only 13 or 14 days a year. So by bringing down that peak to more manageable levels and by making landscape irrigation more efficient, water utility systems are increasingly seeing great peak load management benefits. But what is key is taking a look at the data for the actual individual utility. Generalizations on any statewide basis don't help, because the individual utility has to take a look at what its own embedded energy footprint is. And where there are multiple water supply sources, each water supply source is going to have a different embedded energy footprint. So whether it's groundwater, whether it's surface water supplies, or whether it's an imported supply that has to be conveyed a fair amount of distance, each one of these water supplies have to be calculated on their own merits to see which supply should be is on margin and which supply should be optimized. And so without doing these calculations, a utility won't know what kinds of conservation programs to target. If the problem is a peak demand issue, a water utility needs to take a look at those programs that will help them reduce that peak demand, and those will be cold water programs more than hot water programs. Now, there are a number of models that are available to help a water utility do this. The Alliance for Water Efficiency does happen to have one, and I thought it would be useful to show everyone just so they can see what types of analyses water utilities can do to estimate this water and energy connection in their customer-side water conservation programs. I'm going to show you some quick screenshots from something we've built called the Water Conservation Tracking Tool, which is a very utility-specific model that takes utility inputs and information about their specific system and how it's growing, and then applies water conservation options and evaluates whether those options are cost beneficial for that system. There are 25 programs that are pre-embedded in the model, but new ones can be created. It's a very simple Excel model with dialog boxes that are easy to use. And once programs are selected, and here you can see in this screenshot there are a series of programs that have been selected for demonstration purposes, and then the utility picks how many they want to do in each one of a number of years, and then the model begins to calculate what the benefits are, both in terms of gross and peak water savings and net savings with the plumbing code factored in. So here's a screenshot that shows reduction in service area demands, per capita demands, water savings by sector. There are graphic outputs that show, as in this particular case, how capacity can be extended through the use of conservation activity. That solid black line at about 70,000, 71,000 acre feet is a capacity constraint line, which would be exceeded around the year 2020 with regular baseline demand unadjusted. But once you take a look at what the plumbing codes and standards have provided in terms of benefits, you'll see that that capacity can actually be extended for quite a bit longer into the future, because these free savings from the national plumbing codes largely which are unaccounted for in many demand projections, are actually providing a lot of benefit and reduced consumption to water utilities. Then the light blue line would be the active conservation programs that would be applied that further extend the life of the facility. Same with per capita demands, showing the reduction again in per capita, showing how it affects peak season system capacity. Again, the same sort of analysis. And then what the savings are by customer class across the years, with the code included, and then with the code taken out, so that you know what the effect is of the code and what the effect is of the monetary investment that the utility is making. Many of these models do benefit cost analyses. Ours does one as well. There's the utility costs on the top part of the sheet here, benefits following, and then the ratio of benefits over costs, showing which programs have penciled out to be not cost-effective for the water utility and which ones are cost-effective. So a straight economic analysis of benefit. But tied to that needs to be an analysis of not just the customer-side programs, but also what the benefit is to reducing losses in the system and reducing the non-revenue water. So the model takes a look at what demand-side programs cost and how it compares with a moderate and then an aggressive water loss management program, which is what those pink bars in this particular slide are showing. But to get to the energy part of this, the model also takes a look at where the water utility is located. It plots it by the E-grid region. You select the E-grid region where you're located and get the summary data for how electricity is generated, what kinds of sources are used to generate that electricity in that region. And then the utility answers a series of questions about estimating their embedded energy in their water supply and wastewater, and determining that intensity of both local supplies, the various types of supplies for water supply as well as for wastewater treatment. And then the model begins to calculate what the utility side energy savings are from the conservation programs that were chosen, as well as the customer side energy benefits from those same conservation programs. And then computes what the annual and cumulative electricity savings are for both the utility and the customer, what the annual and cumulative gas savings are for both the utility and the customer, and then lastly, what the emission reductions are from the conservation programs that have been scripted in the model over the period of time that are indicated. So this allows a utility to take a look at the energy benefits as well as the water efficiency economic benefits, and to factor that into their long-range integrated water resources planning purposes. And again, I show you this model because others exist, but it is an important analysis for all water utilities to do, to take a look at what they can cost-effectively fund in terms of incentives for their customers, and also how they can do so without hurting their own bottom line. One of the major concerns for many water utilities is meeting their fixed costs and making sure that they meet their revenue requirement. So one of the things that our model does is it estimates what the changes to the utility revenue requirement from implementing a water efficiency set of programs and giving them the opportunity to evaluate how they can best meet that. In this particular chart, you see that there's some short-term impacts, serious short-term impacts in the first several years from the implementation of the programs, both from the reduced demand and therefore reduced sales, but also the cost of the program, which is usually funded in current operating year revenue. But if the program is debt financed over a 20-year period, which is what the red line shows, it's an overall savings, cost savings for the water utility system. And that's the important piece of information to take away from this particular chart. It depends on how you structure how those charges are paid for over time, and constructing what will be a net benefit for your customers over time. So what does that get us then to conclude? system optimization is a very important activity, and again, the Watergy program has done an excellent job of doing that. But we also must remember that a large energy benefit can also come from customer demand-side conservation, and that can be calculated and can be calculated pretty effectively. And one of the reasons to do that is to take advantage of energy efficiency funding, which is available on the federal level and in some states to fund customer water efficiency programs when that energy benefit can be calculated and demonstrated. And we increasingly are working to make sure that more opportunities are available for funding of water efficiency programs for that energy benefit. And that's one of the recommendations that has been made in a recently released document called A Blueprint for Action. We all know that more attention is needed at the federal level to this water, energy, and nexus. And last December, a large group of stakeholders, including the Alliance to State Energy, came together to examine what recommendations should be made to policy leaders at both the federal, state, and also at the local levels to address these issues related to water and energy. So I invite you to take a look at that report, and there's the URL on our website where you can download it and view it. But we're increasingly wanting to promote the water and energy efficiency benefits on the embedded energy side, as well as better management of the embedded water and energy on the power plant cooling side and siting side. So that concludes my presentation, and I look forward to hearing if you have any questions or if there's anything we can further help you with. The Alliance for Water Efficiency is a nonprofit based in Chicago, dedicated to supporting all stakeholders working to reduce wasteful water use, and we look forward to continuing to work with you. Thank you.
Thank you very much, Marianne. We'll have some question time at the end. Right now, I'd like to introduce Jonathan Gledhill, the President of Policy Navigation Group. And Mr. Gledhill is going to talk to us about putting the actual Watergy program in place in the United States with a case study of the first Watergy project. Jonathan?
Thanks, Bruce. As Bruce mentioned, I'm going to pick up where Bruce and Brian left off. I'm going to talk about particularly how we applied Watergy here in the United States with utility, and talk about how it particularly fits to the challenges that U.S. water utilities are facing right now. Policy Navigation Group is partnered with the Alliance, and our particular focus is finding the funding and for water utilities need to sometimes implement these projects and can take advantage of, frankly, to lower their costs to conserve energy. So what I want to do is talk to you a little bit about the case that Brian mentioned, Bucks County Water and Sewer Authority. For those of you not familiar with it, Bucks County is immediately north of Philadelphia in the eastern part of Pennsylvania. It's a very large geographical area that it covers for the east. It's ranges from sort of inner city to wealthy suburb all the way out to farmland. So it encompasses a wide range of suburban development, light industry, as well as farming. Bucks County is a pretty typical utility, and that's why I think it makes a great case study. It's a nonprofit authority that operates with an independent board of local elected officials. It can reinvest money. It's not a municipal entity. It has about $65 million annual revenues. It serves nearly 400,000 customers in Bucks County and Montgomery County. And just to give you an idea of how it's typical, there's 27 water systems like it in Pennsylvania that serve over 100,000 people. And there are about 1,000 of these type of systems serving over 100,000 people in the United States. So what you're going to see in Bucks County is very typical of an eastern utility and very typical of the enormous amount of energy efficiency opportunities there are at our water utilities across the country. Also, a little interesting about this, and it's common to how water systems have evolved to meet the changing energy and regulatory requirements, that Bucks County has grown by acquisition by taking over smaller, sometimes town or municipal systems over the last 15 years. had an enormous amount of organic growth. So why the typical eastern water system? Well, unlike out west, where there's much more concern about water scarcity and having to bring water large distances, being in the east, the water is pretty readily available. There's some pumping and storage, but it's not a major part of their system. It has high-quality raw water, which is increasingly a rare commodity in water systems. But conventional pretreatment is sufficient, unlike Western systems or many systems where water is scarce, where you have to do extensive pretreatment. Bucks County, like many eastern systems, can do relatively simple pretreatment. And so energy intensity in their pretreatment system is not that big of an option. However, their distribution system is based on history of the way towns evolved over and developed over 300 years, not by a rational grid system layout to deliver water from where it is to where it's needed. So there's a lot of inter-system pumping, pressure zones, and things like that that consume energy that create great opportunities for more effective management. The other thing that really drives their considerations and many water utilities things is that energy is one of their top 3 expenses. And if you talk to water utilities across the nation, energy costs, electricity costs in particular, are often the second or third cost after labor. They spent $1.7 million in 2009, and we're facing 30 to 40% increases in their state for the next couple of years. They're a big consumer. They look like a large industrial facility. They consume over 20 million kilowatt hours, and they asked us to come in at a key point in their management. They saw energy prices increasing. They were facing pressure from their elected board and from the public to be more sustainable and to define what that means. They were also contemplating some large capital projects and knew that they, in response to the energy price increases, the capital projects, they knew that if they were going to justify any rate increases, they had to show their ratepayers in this economically tough time that they had done everything they could to squeeze efficiency and only go to the and ask for a rate increase when they absolutely had to. So they invited us to come in and apply Watergy to their system. So we looked at 4 of their wastewater treatment plants and 3 of their pumping stations as part of this project. Our project looked for 3 elements into the energy management plan. We looked at efficiency in the equipment and the pumping and treatment. We looked at the possibility of generating energy through their system. One of the things I think that is less well understood about drinking water systems is, given their distribution system, there are opportunities to generate power through pressure relief valves, through use of the land area they may have for renewable energy projects like wind and solar. Many water systems operate storage systems that have excess pressure, like you can think of the water tanks that you see in many communities. Well, that water rushes down into the distribution system. There's opportunities to capture some of that potential energy to use to power local needs. And finally, we looked at the human element, the importance of operational controls and training. Do they have the right meters and measuring devices to know what energy they're consuming to fit into an operational plan to give their staff the ability to manage energy in the same way that they manage water flow and water quality. So after some very detailed on-site reviews, interviews with operators, interviews with management, the combined team came up with solutions, some of which is here, some pump controls, some blower replacements, mechanical and metering improvements, and operator training. Finally, we took all those and we said, well, we could pay for all these out of our existing cash flow, but what opportunities are there for financing by government, utilities, and private parties? Right now, just to put in perspective, the traditional source traditional source for water utilities for support has been the Federal Drinking Water Revolving Fund or the Clean Water Fund for wastewater utilities. But in real terms, that money has shrunk by 30% over the last decade. So water utilities are having more and more financial needs and less traditional levels of support. So what we've been doing with the Alliance and with our water utility partners is translate these projects so they meet the criteria of all the funding that's available for energy efficiency projects at the federal, state, at local utility, and even at the private party level. So we did the financial analysis that looked at not just the traditional rates of return from the energy savings, but looked at, do these projects then qualify as energy efficiency projects? So when we do that, we look at the energy savings that the combined package of projects we found for Bucks County will save, $4 million, or basically 20% of their annual energy use, save over $300,000 in operating costs, and their payback is less than 2 years. So they're basically a 65% rate of return on their interest. From a carbon CO2 greenhouse gas perspective, it's equivalent to taking 4,000 cars off the road. The incentive programs we found through the state, through Pennsylvania, through the local utility, greatly improves the payback. Basically, from a financial perspective, the water utility looks at, if I spend $1.8 million, I get $3.2 million back in reduced energy costs and direct payments. So this is a very attractive financial opportunity for the utility. And this is pretty common across the country if you look at the availability of state funding and private utility funding. It's now well surpassing the traditional levels of the Drinking Water Revolving Fund and traditional support there for water utilities. And like I said, it's just the tip of the iceberg in terms of, if we think of from a public policy perspective that I know Bruce will be talking about, if we want to think about where we can get large returns of our energy efficiency funding, both if you're a private entity wanting to promote energy efficiency, if you're a power utility, or if you're a water utility looking to market your energy efficiency projects for these sources of funding. We have about 1,000 large water systems that are out there. We have well over $500 million in private government energy efficiency incentives, and that number is growing rapidly. And water utilities really offer something for energy efficiency funders that are hard to find. Because water utilities can improve their capital, we know that the energy efficiency fundings are real. You can see the capital equipment. Because there's trained staff monitoring them, the energy efficiency reductions are both monitored and verifiable. And water utilities operate 24/7. So it's a much more effective and efficient way to do an energy efficiency project than many of its alternatives. As we say, it's the gold standard for meeting the requirements for an electric utility or a federal agency that's trying to show that they can document that they've really achieved energy efficiency. So we are very excited to be part of this, to show this enormous opportunity that's out there for water utilities, not only to reduce their operating costs, but help find partners that can defray those costs to further so we all can get the environmental and energy benefits from reduced energy consumption.
Thanks, Jonathan. That was really good. Just wanted to go over one little addendum of the energy project over at Bucks County. One of the things we wanted to point out is that the approach that we use with Watergy is what we would call a best practices approach. As Jonathan mentioned, we really sought buy-in from the plant personnel at all the sites of Bucks County. So we started with a collaborative approach. We included various levels of management as well as operations, and we took on-site measurements of the energy uses rather than sitting at a desk and calculating theoretical energy savings using nameplate data. We actually went on site and examined the entire systems from top to bottom to derive the energy savings estimates. Another big part of our approach is that we are technology neutral and product agnostic. The Alliance to Save Energy and Policy Navigation Group have no financial interest in any of the equipment purchases that may happen if Bucks County or any other utility were to implement some of our recommendations. And then fourth and really biggest, most important component of this is our knowledge of energy management. When we went through the assessment, we applied the principles contained in the now released ISO 50001 Energy Management Standard, and also one of our experts was one of the prime contributors to the American Society of Mechanical Engineering System Assessment Standard for pumping systems. So we really applied the best practices of energy assessment and energy management to this project. A few policy implications that we've noticed so far from this and this project and a few other conversations we've had is that for water and energy utilities, there is a need for better coordination. A lot of times these communities, the water and the electric utilities, don't talk to each other very much, or if they do, sometimes they don't talk to each other very well. So there is a need to raise awareness in both camps about the end-use needs of energy and water for both of them and how they can use them more efficiently. Regulatory structures, there could be more incentives for water and energy efficiency, particularly at the end-use level, but also at the supplier level. There are codes that can yield better efficient water delivery and treatment. Right now, there are still some homes in the United States that are made with polybutylene piping. That was a disaster for a lot of homeowners and something that needs to be upgraded. Finally, also, there's some voluntary programs that can be leveraged that use energy management standards, particularly Energy Star at the EPA, and then a new developing program called Superior Energy Performance from the U.S. DOE. Financing is also an important application. There needs to be more access to capital, particularly for the assessment services, as well as energy efficiency implementation, and perhaps also accelerated depreciation of energy efficient equipment. A few other areas where we've been working in terms of Watergy and taking the program, we've begun to establish some collaboration and partnerships with various key stakeholders in the industry, particularly the Alliance for Water Efficiency, the American Water Works Association, the National Association of Clean Water Agencies, and the Water and Energy Foundation. I would point out that the Water and Energy Foundation is having their first annual Water and Energy Conference this summer in Chicago, and they've extended the early bird registration rate for anyone who's interested. It's up until tonight at midnight. We also engage in some advocacy about water and energy efficiency at various conferences and workshops that we attend. We make presentations, or we're working on some white papers that we're going to present at upcoming conferences. And training has also been a big component. We're developing courses based on the principles in ISO 5001. These courses are going to include introductory and advanced levels for operators as well as for management of water and wastewater utilities. And we also look to leverage a lot of the DOE and EPA programs, including Superior Energy Performance and Energy Star. Another thing we like to do is promote the ASME System Assessment Standards. Right now, the main assessment standard that pertains to this industry is the Pumping System Assessment Standard. We are recommending that DOE produce, or the ASME, I should say, look to produce a standard on industrial fan systems, and that would then pertain to the aeration blowers that are found in wastewater treatment plants. A couple other items on program and policy development. We do recommend at the federal level that Superior Energy Performance and Energy Star pay more attention to the water and wastewater utility industry. We are also supporting the development of the blueprint document that Mary Ann Dickinson talked about earlier, as we think this will be an important tool to raise awareness for policymakers about the importance of water and energy efficiency. And also in the training area, we recommend that energy efficiency be included in water and wastewater utility operator curricula. Right now in the United States, there is, in some parts of the country, a shortage of trained sewer operators, and it's not clear whether the training that the few sewer operators who are out there get includes energy efficiency. And so this would help go a long way towards getting that low-hanging fruit that is found in a lot of energy assessments. A few words on future water activities. or Watergy activities, I should say. We are looking at more projects with additional utilities and state agencies. We do intend to perform more policy and program development, and as well as more outreach and training. We think that this is a very important part of raising awareness and amplifying the message of water and energy efficiency. At this time, I think that we should talk to Grant Van Hebert from Schneider Electric, who is going to give us a presentation on the opportunities more generally in the market. Grant?
Greetings. How is everybody doing? Yes, this is going to be I think a quick presentation because we need to get on to the point of the question and answer session. So I've got about 21 slides here. I want to run through relatively quickly. Let's start back in 2003. We use a marketing company internally within Schneider called Frost & Sullivan, and they went out to several thousand water wastewater utilities and asked them exactly what their concerns were and what they looked for when they were purchasing something. And, of course, the number one concern was reliability, but I want to come down here to number 7, which is actually the operating cost. Operating costs, in other words, energy, chemical spend, and all that was in the last 50%. Actually, it was number 7. So you can see it was not one of their primary concerns when they purchased equipment. And, of course, that has a direct implication of they're not looking at operating costs, they're not looking at efficiency, and they're not looking at the motors, they're not looking at the blowers or the way they're actually running their treatment processes as a concern when they're purchasing something. But what we've seen since then is a pretty large change. First there was Katrina, then the Gulf oil spill, been concerns coming out about global warming. The economic collapse had an impact on the municipalities' tax bases, and then of course there's been governmental awareness on top of that. Back in 2009, Jeanette Brown had a conversation in front of a House subcommittee on energy efficiency. She works for WEF, by the way, if you have not heard of her. And then the EPA moved and expanded the Energy Star program into water wastewater. So all of these impacts together has really changed the way that we have seen municipalities looking at energy. That's not to say that we at Schneider Electric are seeing every municipality look at energy. I'm out with municipalities all the time, and you still find it amazing how many people I talk to that say, well, I'm the facility manager, but my electric bills come in and go to the accounts payable person, and I never see them. So sometimes you just need to make people a little bit more aware of what the energy actually is. But the world itself is really changing overall before our eyes. We're starting to see more increased demand for energy. Of course, there's limited natural resources, limited capacity, environmental concerns. And what this is driving and pushing towards is a worldwide increase in energy of basically doubling the energy by 2050, while at the same time we're going to have to decrease our CO2 emissions by about 50%. There's a variety of ways that we need to do this, but what it basically comes down to is we have to do this now. This is not something that we can wait upon. So to tie this down into water wastewater, what are we actually seeing as some of the challenges, at least on the Schneider Electric side? We're seeing what was touched upon before, water scarcity. More than 35 states are anticipating water shortages by 2013. Seeing some stuff on climate change. It's going to significantly adapt the way that we maintain and utilize our infrastructure resources. Increasing population. Energy uncertainty. The depletion of our traditional fuels, being gas, oil, coal, so on and so forth, is really causing instability in the energy prices, and that makes it very tough for utilities to actually create a stable budget, which, as we all know, that's something that is key of importance. And then, of course, aging infrastructure. The interesting thing is that by 2031, it's going to cost somewhere between $300 billion to $1 trillion to repair, replace, or upgrade the facilities out there. Another thing that we are seeing is shown here on this slide. We're seeing water prices of desire to stay relatively constant. Your human resources costs are going up, but nowhere near the amount of energy price. And what we've seen is HR costs are somewhat political. Whatever party is out of power, if the treatment plant cuts back on staff, the out party, shall we call them, will use that as a political leverage to try and regain power. You know, so-and-so is laying off all these good jobs in our local community, that type of thing. So really HR brings with it a political cost, but no one no one is concerned about lowering energy costs. There's not a political downside on that, is what I'm trying to say. So this is what where we really see a focus on, is people want to get rid of the energy and lower the cost. There's only a political upside for doing that. And really what we're seeing, and this has been touched on before, is $4 billion annually is spent for energy, and it's about 1/3 of municipal energy spend. What's interesting here is when you consider a large municipality, let's take perhaps Indianapolis or Chicago or New York, and you realize how many fire departments are out there, police departments, schools, other government buildings, the energy usage into all of that, and then add in all the stoplights, and that only comes up to basically 2/3 of the city's energy usage. 1/3 is running in the water and wastewater areas alone. Looking at 10% reduction, we save $400 million, and this is the interesting thing, 5 billion kilowatts annually. That's enough, if we actually pulled it off, to be able to cancel construction of power plants, or maybe to shut some down that are reaching the end of their life. So that's significant. Now, another thing I want to point out here is this 25.1 gallons to generate 1 kilowatt hour. And I want you to remember that. That actually comes from IEEE, believe it or not. They took a look to see what the energy, what the water usage was in energy, and they came up with 25.1 gallon average for 1 kilowatt of electricity. So, of course, we apply that into the 5 billion kilowatts annually saved. We come up with 125.5 billion gallons saved at the power plant. And as we saw in the previous graph, about 49% of the water that is being used is going into power. So that's quite a significant number here. Well, let's take a look at some current drivers and trends. And I want to focus you down to these two graphs in the bottom, much more than the stuff up top. This is, I will admit, this is a reused slide. So what's talking about here really doesn't, up in the top, really does not go to where we want to go. But the bottom two does. This is exactly what we see as being where the water usage is, or the energy usage is in water, which a total of it is 87% of it is going to pumping, whether it's distribution pumping, raw water pumping, or actually in-plant pumping. Now, the interesting thing is we see that as chlorine becomes more and more regulated, we actually see more utilities going towards UV and ozone, which is actually going to increase that 11% that is dedicated to treatment process. So we see some things coming along here that's actually going to increase the yield. But really, for the most part, pumping is where you go for water. Now let's take a look at wastewater for a bit. Process, 91.9%, with about 54.1 on the facility that we're using it as an example, going to aeration. I remember seeing the graph earlier today that showed a little bit less, but the point is aeration is clearly the largest user. And when you think of it, if you've got surface rotors, that's a different thing. But if you've got blowers, a blower is just a device, whether it's positive displacement or centrifugal, to move air from one point to another. Very similarly, a pump moves liquid from one point to another. So when it comes down to our world out of Schneider Electric, looking at automation, control, and power, there really is no difference between a pump and a blower. So we can really look at the blowers as a type of a pump. And therefore, we realize that 54.1% in aeration is controlled by a pump-like device. Plus, some of the other processes will also have pumps to move sand around or move grit around or that type of thing. So there's other pumps throughout the wastewater process, but clearly aeration is where you go. So how do you save energy? We see it as a three-part approach. First, energy efficiency. You lower your demand via energy use reduction, but that's not going to get you to heaven. That is only part of it. The other thing you have to do is lower your demand response. So you lower your demand via load shedding. Perhaps if your wastewater plant, you can take your sludge pressing operations to the nighttime instead of during the day if you get higher energy rates during the day. This is another aspect. It also preserves grid integrity and saves resources. The way that the power companies work is this. They will monitor you over time and say, okay, monitor you for 90 days. On this one day in June in the afternoon, you use 2 times more energy than you normally do. So therefore, to make sure that you can do what you need to do, we have to make sure that we supply over that 90-day period of time or that year period of time double the amount of energy available at any given moment. So if you lower your demand, the utility can come back and go, okay, we know you're going to use less energy, and by adding that with yourself and all the other energy users out there, they may be able to say, you know what, we don't have to produce 100 kilowatt hours now. We can actually produce 95 and still keep the load happy. So the utilities will have demand response billing into your bills that, for lack of a better term, punish you, or they make you pay for high demand response, so you want to lower that. And then the third way of lowering energy is through the use of renewables. So you're using local power generation from non-depleting resources. Solar, wind was touched upon. Also using biogas is another way. I just found a valve manufacturer while I was at ACE a few months ago, actually a few weeks ago, excuse me, that is actually using the water that is going through their valves to generate electricity off of each valve. Not a lot of electricity, but it's designed to be accumulated, so either you can run a local control station off of it, or you can build it up through 2 or 3 valves and actually take it somewhere to store it for later use. So you've got some people that are doing some pretty innovative things out here. Another thing to talk about is the energy savings ratio is actually 3 to 1. We're at what this chart is actually showing is, let's say we're using coal, and the fuel is irrelevant. The same type of efficiencies come in. So you got 100 units being created by coal or gas or whatever you're burning. About 1/3 of that is lost in the plant manufacturing, or in the power plant. So in other words, the coal has 100 units of energy, or your fuel has 100 units of energy. By the time you come out of the plant, you've had a 30-some-odd% reduction in energy. So you're only releasing about 65 units of energy to your distribution grid. Then once you come off of that, once you go through that grid and you go through all the transformers that you step the power up, step it down, your line losses, and all those are calculated in, you're going to lose about another 33 to 35% of energy. So basically, for every 100 units that's produced, only about 1/3 will reach the water or wastewater facility. So therefore, 1 unit saved at the facility equals 3 units saved at the plant. Now, we tie this back into this water figure that I told you before, 25.1 gallons per 1 kilowatt hour. If we actually save 1 kilowatt hour at the facility, by the time we multiply that by 3 and then convert that to gallons of water saved, you're actually saving really 75.3 gallons of water. So we talked about how much of the water is actually being pulled out of a variety of resources to go into energy production. And here what we're saying is if you're a water utility, if you save 1 kilowatt hour, you're dramatically decreasing the amount on the other side. And as we all know, a lot of water utilities have programs to save water through either low-flow shower heads or irrigation sprinkler flow limiting devices, that type of thing. But let's talk about how do we save energy directly. And as we see, the fastest way to do it is through a 4-step process. And the number one, we believe, is really about the most critical, because without number one, you can't do the rest of it reliably over time, and that is to audit and meter and measure your energy. Now, it has to be what we call active energy management. We have a lot of systems, as do our competitors, that have been put into distribution centers as far as power distribution equipment to monitor energy usage. So what happens is although these systems are put in to monitor the energy, to monitor the power and all these power meters, they are actually just sitting there. And they are not integrated in necessarily with the process SCADA. So therefore, you can go up to a utility person, you can say, can you tell me what the dissolved oxygen is in Basin 3? And he can tell you because he'll look on the SCADA system and he'll find it. Then you say, can you tell me what Basin 3 was doing on dissolved oxygen at this time of day 3 weeks ago? Once again, he goes into the trend logs and he can find it. Now ask him the question of, okay, when you were at that energy 3 weeks ago, and you were at that same, dissolved oxygen at 3.0 3 weeks ago, dissolved oxygen at 3.0 today, what was your energy usage 3 weeks ago compared to now, even though the dissolved oxygen was the same? And that's where a lot of utility people will just stop and go, I don't know. To do that, I need to go over to this other software. And so that you don't see a lot of tie-in here. And so without looking at energy on a constant basis, you will actually not realize what you're actually doing as far as energy spend. And if you do save energy without continual monitoring, you may fall back into bad habits and lose that efficiency over time. The second one is to come in and fix the basics. That is to take a look at some of your devices and put in low-consumption devices, change your power quality, increase your power reliability, then optimize through automation. Really sit down and look at your process, look at your power, your motor control, your lighting, and really start to push those things forward as far as innovative solutions. A lot of the things they were talking about in the earlier presentations with the Watergy is what we're talking about under level number 3. And then number 4, continued monitoring and consulting services. Monitor, maintain, and improve. And when you do number 4, you will actually find yourself back at step 1 again, and it's a continual loop. And that's kind of how we see that this has to be done over time. Now, remember what I had said about pumps and water or blowers being pumps and wastewater. The interesting thing is when you really look at the life cycle cost of a pump, and the same goes for a blower, 40% of it is for energy. But what we see so often on bid day is that the focus on bid day is what does that pump actually cost? Is this pump $10 cheaper than another brand pump, and is it going to do the same thing? There's so much focus on this, but no one ever says, okay, brand X is $10 cheaper than brand Y, but does brand X have a higher energy spend over the 20-year life cycle of a pump? No one ever asked that question, or very rarely is that ever asked. But at the end of the day, what is being paid for by the municipality is the energy. So how do we reduce energy? Well, you've heard talk, and you will probably hear even more talk about VFDs saving energy. And they are a very important tool to assist you in saving energy. But all of the variable frequency drive is a power converter. You take a voltage current coming in at 60 hertz, or if you're in a European country at 50 hertz, you convert that over to DC, and then you reassemble it at whatever frequency you want. So it's just a power converter. It doesn't really save you too much energy directly. Where the savings comes in is in something called the affinity laws. Now, these are really designed to affect centrifugal blowers and pumps. You got a positive displacement blower and pump. They do save you energy as you reduce the speed, but that is affected by a completely different set of rules that we're not going to cover in this PowerPoint. So really what happens is that the affinity laws will find the impact of varying speed on flow, pressure, and power. And here's what it basically says. Your flow will change proportionally with a change in speed. Likewise, your pressure changes by the square for a change in speed. Now, this is really the devil in the detail, because as you back off on a blower, you back off a pump application, you really have to look at your discharge pressure and make sure that that pressure is still high enough to be able to do the work that you are trying to do. But here is the real sweet spot. Power changes by the cube. So what this basically means is a 20% reduction in speed can give you a 50% reduction in power. So as long as you can keep your pressure up, you can see dramatic energy savings. And this is where the magic of the VFDs actually come into play. The interesting thing here is that if you have two pumps running at 80% capacity, then 80% plus 80% is 160% of your pumping capacity. But your energy usage would actually be that of one pump running at full speed. So think about that for a while. It's not really truly free energy, but on your power bill, it's not going to know the difference. We've actually got 3 or 4 different things that we try to apply whenever possible and talk to various clients about, whether it's advanced water network management, water network integration security management, power management within process SCADA, or process optimization. I want to talk about each one of these a little bit and also show somewhat of a case study. But first off, water infrastructure monitoring, where you're reducing the water linkage and distribution. We do understand that water leakage is huge as far as energy wastage. The point was made earlier and that if you produce, if you spend the money to produce and pump a gallon of water, and that leaks out of the pump and goes into the soil, sure, somebody's petunias are quite happy, but at the end of the day, you've just wasted a lot of effort to treat a gallon of water that is not going to be used as it was intended. One of the things here was eliminate the bad meters and then kind of really find out where the loss is actually going on. So one of the things we did at this facility over in Europe, the city, is we started off with 2 months of infrastructure monitoring of their more than 2,000 miles of distribution piping. And what we found was this. There were 62 metered districts, as they call it, or DMAs, that were traced out. Found 78 faulty meters and dozens of energy events. Found 49 unknown leaks and actually detected 17 bursts within 2 hours advance notice. In other words, started to see certain things going on in the distribution system that led people to see, after understanding the data, that, hey, we're going to get a burst here. We better go out and take care of it. Solve some blind spots, repair verifications, non-operable DMA alerts, and zonal alerts, and then led towards maintenance prioritization, meter placement, and acoustic surveying timing. In other words, we would be able to know, okay, this DMA's got a leak in it. Now you could go out with your acoustic tools and trace it down, where before you might have had to have been at the mercy of a larger acoustic testing program. Please forgive me for a second, I have lost my mouse. There it is. Water distribution, network energy optimization, reducing your energy bill, carbon footprint. But once again, this is really looking at a distribution system and trying to model it for its efficiency, so that if you've got a large system, instead of pumping a whole bunch of water over into Zone 1, you might be able to back off the pumps into Zone 1 and let the overflow in Zone 2 or Zone 3 actually flow back to the system and take care of the need. So doing this type of system-wide modeling. And we were able to, in this one facility, demonstrate energy and carbon footprint up to 30%. And here's kind of what we saw here. The system fact was, the system we looked at here is 68 million gallons a day, 165 million gallons a day peak in the summer. So this is actually more of a larger resort type of facility. 5.5 million in distribution pumping costs, 2 water plants, and you can read the rest of it. What we did was we put an automatic hydraulic optimization algorithm on top of the control system. 14 pump stations, 62 pumps, 10 flow valves. You can see how that all works out. And the benefit, 20% lower energy costs, and reduced peak summer demand by 4 megawatts. So that is quite significant. And the results were well beyond what we had anticipated. Similarly, we took a look at an activated sludge plant over in a European city. And the interesting thing is that with activated sludge, we're typically looking at dissolved oxygen as the driving point for either the blowers themselves or the blowers and zone valves that are located close to the sensor. And dissolved oxygen is really almost like a secondary parameter. In other words, once you understand how your plant behaves, you can derive a good dissolved oxygen set point. That you set for control, and you let the blowers go for that dissolved oxygen point. But what we've got is a way to look at about 20 to 30 different other parameters going on within an activated sludge plant and say these are the parameters that are critical, and as long as we maintain these other parameters, then dissolved oxygen can be basically anywhere. And we will drive that dissolved oxygen point wherever we need it to be and drive the blowers wherever they need to be to meet all of the rest of the critical demands. And so what's happened here is that we are seeing a reduction. Once again, at this case study, the first thing we did was we pulled off the finite limits on the dissolved oxygen, such as 1.5 milligrams per liter as an upper limit and no less than 0.5 milligrams per liter. We did this once again by controlling the inlet and outlet quality parameters of the water and saying, so what if you've got 0.3 milligrams per liter of dissolved oxygen going into the system, as long as the rest of the parameters that you need to treat are being maintained, then that's also okay. Likewise, we have to go up to 2.5. We can do that too. Another thing we did was the aerator control on sensor failure. Because of monitoring other parameters, we're able to actually look back through history and reconstruct a missing signal. So in other words, your dissolved oxygen probe goes out, we can reconstruct that, and therefore we're able to eliminate the fail to full aeration mode, which, as you know, if you've got a bad dissolved oxygen sensor, you go to full aeration. So because the theory is it's better to over-aerate than to kill your biology. And we're now able to eliminate that. The other thing is aerator operation controlled more effectively by matching the DO and feeding forward. In other words, we're seeing something coming in. It's at headworks now. Let's go ahead and start to react for it before it actually hits the ASP part of the plant. The result was up to 35% lower energy, which equates to 0.75 kilowatts per kilogram of BOD. Carbon reduction was about 260 tons a year, and the project ROI was about less than 18 months. So we got about as close to optimal ASP performance as we could. And that is the end of my presentation.
Well, thank you very much, Grant. That was an illuminating presentation. I'd like to have Brian Costelli give a few concluding remarks, and then we'll take some questions.
Yeah, I'm going to make these concluding remarks pretty short and to the point. You can see the first one up on the slide. Water and energy aren't cheap or plentiful. Clearly, water's become more scarce as drought conditions have been experienced in the past 5 or 10 years. Grant mentioned, climate impacts, and clearly areas of drought are becoming even more impacted, and drought is more severe. Weather conditions are more severe. Energy costs, likewise, in the last 5 or 10 years have continued to climb, and we don't anticipate that in the next few decades they're going to get any cheaper. Second point is addressing water and energy efficiency yields multiple benefits. Again, water and energy efficiency improve the reliability of the grid and the water infrastructure. And it frees up funds for other municipal projects, as I mentioned before. That's a really critical item, because you've got municipalities, cities, counties that are spending too much on both water and energy, more than they should, because they aren't efficient, and that money could be used for other municipal benefits. Finally, there are a lot of opportunities in the U.S. to really transform the water and energy market. The water-energy link is clearly critical to the bottom line of city, county, and private water utilities. Increasing the market penetration of energy-efficient technologies is really an area that has great opportunity in the U.S. For example, Grant mentioned variable frequency drives. In the U.S., we only have about a market penetration of about 9% of VFDs in the industrial area. In Europe and Japan, they have 19% and 38% respectively market penetration. And that's just tremendously higher, much more efficient, and they save a lot of money. Fostering a culture of continuous improvements in energy and water efficiency is really important. Our trainings work to get operators at the plants to embrace such a culture. Energy efficiency is often done in response to a sudden high energy price or an equipment failure. But continuous improvement leads to lower long-run energy costs and variable production and delivery of water, a reliable production in both delivery of water and energy. So I think that we've heard a lot of good things today, and I'd like to open this up now to questions from everybody on the line. And apparently we're getting this set up right now to take on questions.
All attendees have been unmuted.
Hi, Brian.
Okay. I'm sorry. You're now all open to ask questions.
Hello, Brian.
Yeah.
This is Christopher Russell. How you doing there?
Chris Russell, how are you?
I am doing fantastic, and my question for you and the crew there is, what is the Watergy program's experience with improving the metering technologies at the consumer end, because that is one of our biggest opportunities here in Howard County.
Thanks, Chris. As far as the metering, for residential, we haven't seen too many big changes over the last several years. What we have seen, to the contrary, though, is the technologies for leak detection within the piping mains. 30 years ago, you had to have a technician open up a sewer hole and go in there and check for leaks manually. Now, this can be done remotely with wireless technologies that can sense longer areas of the pipe. So that's one of the big areas that we've seen that's improved it. Hopefully that answers your question.
We'll talk tomorrow. More on that, Bruce. Thank you.
Other questions?
We did see that there were some questions sent in through the chat function, and one of the most common ones is whether these presentations will be available at a later date. We can say yes, they will be available to all the people who RSVP'd to this webinar, and we'll let you know when it's available and how to access it. Oh, there's a question for the AWE. I think Mary Ann has had to unfortunately leave our room, but I think Bill Christensen from AWE is on the line, and the question is, thank you very much for the overview of AWE spreadsheet tool. Is it available at no cost for use by non-AWE members? Bill?
Yeah, unfortunately, it's only available to our members. We do provide it free of charge to our members. It's one of the benefits we can provide them. And if you are interested finding out what your dues would be and some of the other member benefits, you can go to our website within Mary Ann's presentation, URL, and you can also just Google Alliance for Water Efficiency or give us a call as well if you have any further questions.
Okay.
Thanks, Bill.
I have a question.
Sure.
Can you tell me, there was a 25.1 kilowatt hours or 25.1 gallons per kilowatt hour number that was attributed to IEEE. Do you have any reference on that?
Yeah, this is great. Let me pull up the PowerPoint on my computer, and I'll come back in a moment with that answer. Hello? Okay.
While we're waiting for Grant, does anyone else have any questions offhand? Or?
Okay, here's the website. HTTP, obviously, how-much-water-does-it-take-to-make-electricity.
Did you get all that?
Well, more or less. There was another question related to another fellow I was talking to, and there was a 75 gallons per kilowatt hour mentioned versus 25. Can you clarify?
Yes. What it is that the IEEE basically says that for every 1 kilowatt hour that is saved in production at the power plant equals 25.1 gallons of water that is saved. Okay? We're on the same page?
Yes.
Okay. But through the other slide that I showed, I was able to illustrate that for every 1 kilowatt hours that is saved at the water facility, equates to 3 kilowatt hours that is saved at the power plant.
Okay, you're attributing losses to that.
You got it. And so therefore, for 1 kilowatt hours that is saved at the water or wastewater facilities leads to 75.3 gallons that is saved at the power plant.
Okay, thank you.
I think we still have time for a few questions if anyone else has any. Well, I'd like to thank everyone for signing up to our webinar. We actually had the maximum number reached on the RSVPs, and so we hope that we'll be making this available, not only presentations perhaps, but perhaps also the broadcast. And we are looking at possibly doing some future webinars in the future. So if this topic is of interest for you, we'd like to have you join us again.